Hi everyone, this is the last topic. So this is normal distribution and it's for the International Baccalaureate Maths Standard course. In this topic we're going to look at continuous random variables, the normal distribution, probabilities, standard normal distribution and z-scores, and then quantiles. So we learnt this in the last topic. A random variable is the possible outcomes that could occur from some random experiment. A discrete random variable takes distinct possible values, and that's what we were covering in the last topic. In this topic, we're going to look at continuous random variables. They take their values in some interval on the number line. So for a continuous random variable, capital X, little x can take any real value, not just integers. And this is what we write. This means the probability that x lies between A and B. Now for a continuous random variable, the probability that x is equal to an exact amount is 0. So we can't say, for instance, that my height is exactly equal to 170.2 centimeters. Okay, it's always going to have been rounded to that. So it's not exactly equal to 170.200000000 with all the zeros go off to infinity. And that means that the probability that x lies between A and B is actually the same as this. Okay? It doesn't matter whether there's an equal sign, and that's really different to the last topic that we did. All random variables have a corresponding probability distribution that states the probability that the variable has a particular value. For a continuous random variable, we use a probability density function, and this defines the probability distribution. And this is what it is. The probability that x lies between A and B is going to be the integral between A and B of f of x dx, which of course is the area under the curve. Now, many naturally occurring phenomena have a normal distribution, like weight, test scores, blood pressure, crop yields, and height. Here's a graph of the heights in inches of American women. You can see the bulk of the women have heights in here. We have some very tall women and we have some shorter women. But there can be extremes. So we're going to find out shortly that almost all humans lie within 3 standard deviations of the mean. These two don't. So here we've got Robert Wadlow on the left, and he stood at 2.72 meters tall, or 8 feet 11 inches. And the lady on the right is the shortest female ever recorded, and she was 63 centimeters. So both of these would lie outside of that 3 standard deviations from the mean. Now, if x is normally distributed, then its probability density function is given by this horrendous looking thing. Let's have a look at it. F of x is equal to 1 divided by sigma, which is the standard deviation, multiplied by the square root of 2 pi, e to the power of negative a half, and then x take away mu, which is the mean, divided by sigma, all squared, and its domain is negative infinity to positive infinity. And this is what we write. X is distributed as a normal distribution, and this time the two parameters in the brackets are the mean and the variance. Remember, with binomial distribution, it was the number of trials and the probability. So this time it's different. So we've got our mean mu, and they write the variance here rather than the standard deviation. Variance is just standard deviation squared. You'll also find that they quite often write it in index form, like 2 squared or 3 squared, and that's so that you can easily see what the standard deviation is. So all that means is if we draw that, we're going to get a normal curve like this. Now here's the beauty of the normal distribution. Almost all of the data lies within 3 standard deviations of the mean. So let's have a look what that means. So here's our mean here. If I add a standard deviation and subtract a standard deviation, then in here 68% of the data lies in here. So most of the people, if you think of the height example, are in between here. 95% lies within 2 standard deviations of the mean. So almost everybody lies in here. 99.7% of the data are within 3 standard deviations of the mean, so underneath here. Here's an example. A manufacturer produces 1,500 boxes of cereal every day. The weights are normally distributed with a mean of 502 grams and a standard deviation of 2 grams. Right, what does that mean? So this center point here is going to be 502. This is 1 standard deviation above and below. That's 2 grams above and 2 grams below. See how I got that? This is 2 standard deviations above and below. So I'm going to add 2, subtract 2. And then finally 3 standard deviations above and below. Add 2, subtract 2. Only cereal boxes with a weight between 498 and 506 are sold. Find the probability that a box of cereal chosen at random will be sold. And so that's all of the ones between here and here, which is 95%. Look how we've written it. So the probability that X lies between 498 and 506 is equal to 0.95. So on the calculator, we go into stats and then into distribution, which is F5, just like we did before. But this time, instead of binomial, we want normal, which is F1. And again, just like before, we've got 2 options, NPD and NCD, and inverse normal, which we're going to use this time. We want NCD because this is a continuous variable, so F2. So here's the example we just did. Only cereal boxes with a weight between 498 and 506 grams are sold. Find the probability that a box of cereal chosen at random will be sold. So we're going to enter the mean, 502, standard deviation 2, enter 498 for lower and 506 for upper. Here it is here. Lower is 498, upper is 506. Be careful here. This is back the front to what you expect. You expect mean to come first and then standard deviation. So I'm always putting it in, upside down, and then I get a stupid answer. So this is standard deviation here. That's 2, and mean is 502. And then hit enter, or EXE, sorry, and we get our probability as 0.95, just like we did before. Here's another example. A machine manufactures bolts with radii that are normally distributed with a mean of 13.4 millimeters and a standard deviation of 0.2 millimeters. And this is what we write. X is normally distributed, mean 13.4, standard deviation of 0.2 or variance of 0.2 squared. So that's the standard deviation squared. You'll find it's quite often written like this as a squared value rather than 0.04. What percentage of the bolts have a radius greater than 13.75 millimeters? Now, the problem with this question is that we have a lower bound but no upper bound. So let's just think about that. Here's our normal distribution, and our mean is 13.4, so 13.75 sitting here also. And we want this bit here. So we've got a lower bound, which is that, but no upper bound, that's infinity. So we've got to put the largest number in that the calculator will allow, which is 10 to the power of 99. So we just type EXP and then 99, and that will go in there. If you can't remember that, put a really, really big number in, like 1,000 million. That'll be fine. And when we hit execute, we get a probability of 0.0401, roughly. Now, if we want this side, so the left-hand tail, then we're going to have an upper bound but no lower bound. And in that case, we'll type negative EXP 99. Here's a past exam question. The random variable x is normally distributed with a mean of 100. The following diagram shows the normal curve for x. Let R be the shaded region under the curve to the right of 107. The area of R is 0.24. Write down the probability that x is greater than 107. So that's just this area here, which is 0.24. Nice easy question. B. Find the probability that x lies between 100 and 107. So we know that the mean is 100, so we can draw that in. That's this peak here. And between here and infinity lies half the values. So that's 0.5, all of that. So to find this part in here, we do 0.5 take away the part that we have, which is 0.26, so that's the probability. And finally, find the probability that x lies between 93 and 107. So let's put in 93, roughly where it belongs. We can see that this is symmetrical. This goes up by 7 and down by 7. It doesn't mean it's a standard deviation, but we know this area. We just worked it out. So normal distributions are symmetrical. So this is 0.26 as well. So our answer here is going to be 0.52. Now, every normal distribution can be transformed into the standard normal distribution. This is also called the Z distribution. And we use this transformation. You're given this formula on the formula sheet. Z equals x take away mu, all divided by sigma. Now, the Z distribution has a mean of 0 and a standard deviation of 1. So that is, Z is distributed as a normal distribution, mean 0, standard deviation 1. Now the probability density function for the Z distribution is this thing here. And all I've done is put in mu is equal to 0 and sigma equals 1. It gives us the same sort of looking graph. The beauty of it is, instead of having rather ugly numbers down here, depending on what the mean and standard deviation are, we've got nice numbers, 0, 1, 2, 3, -1, -2, -3. Percentages stay the same. So we call these Z scores, and Z will be the number of standard deviations that the original score is away from the mean. So if you're sitting here, it means you are 1 standard deviation below the mean. And we can convert any normal distribution with mean mu and standard deviation sigma to a Z distribution by using this formula. So x is the original score, mu is the original mean, sigma is the original standard deviation, and z is the Z score. Here's an example. Sam received 17 out of 20 for his internal assessment. The class have a mean of 14 and a standard deviation of 2. Between which two values does 95% of the class lie? Okay, so we know that the mean is 14, so we can write that in. And then we know the standard deviation is 2. So I'm just going to add 2 and go up here. And then below the mean, I'm going to subtract 2. And so to answer the question, between which two values does 95% of the class lie? That's in here. So between 10 and 18. The teacher converts the results to Z scores. What is Sam's Z score? So we're just going to use this formula. This is x take away mu divided by sigma. So that's Sam's score there. We're going to take off the mean of 14 and then divide by 2, and that's going to convert it to a Z score. So what's this mean? He is sitting 1.5 standard deviations above the mean. So he's doing pretty well. The teacher feels she has been too tough on her marking and decides to scale the marks to have a mean of 16 and a standard deviation of 1.8. What happens to Sam's results? So now we're going to take our Z score and we're going to put a new mean and a new standard deviation in place. So there's the Z score. There's Sam's new score. There's the mean of 16 and the standard deviation of 1.8. We've just got to solve this equation. Take your 1.8 over. It becomes 2.7. I've switched it around. And now take the 16 over. So his new score is 18.7. So his mark has gone up by 1.7. Here's another way we can use the normal distribution. Sashi receives the following marks for the semester: 88% for maths, 92% for physics, 85% for English. Now, because they're all composed of different assessments, we can't say with any certainty which one is better. It looks like physics is the best mark, but they might have been easier tests. We don't know. So one thing we can do is look at the means and the standard deviation. So this is giving us a centre of the data. We can see that the physics test was easier. And this tells us how spread out it is. So what we're going to do, given the means and standard deviations for the classes, which mark is her best achievement? So we have to convert them to z-scores. That's going to standardize them to a mean of 0 and a standard deviation of 1. We're just using this formula. In the first case, x is 88, mu is 75, and sigma is 11. And putting that in, we get 1.18. So what does that mean? For maths, Sashi was 1.18 above the class mean. Not too bad. Now let's check out physics, putting in the marks. 92 take 80 all over 9, 1.33. So this one is indeed a better result than that one, only slightly. But in this case, she is further above the mean than here. And then finally English, putting that in, 1.08. So that's not as good. That's actually her worst mark. So by standardizing them, we're bringing very different things into a common system so that we can rank them. Okay, one more example. So back in the olden days when I went to school, that's a picture of me in year 11, I think, test scores out of 100 were standardized to a mean of 60 and a standard deviation of 12. Now mostly this is not done anymore, but what that meant was that all of the scores, almost all of them, lay between 24 and 96%. So here's the question. Karen received 72% for her final year 12 assessments. If the class had a mean of 55% and a standard deviation of 8, standardize her score to a mean of 60 and standard deviation of 12. So what we have to do is go via z-scores. Okay, we're going to have to standardize that 72% to a mean of 0 and a standard deviation of 1. It's just a matter of using the formula. So 72 take 55 divided by 8 gives us 2.125. Now we've got to undo that z-score. So the 2.125 is going to go in here. Here's the new score, the standardized score. Mean of 60, standard deviation of 12. Okay, it's just solving an equation, isn't it? X takes 60 equals 25.5. So the new standardized score is 85.5. Okay, last section. Now remember that a quartile is when we take the data set and we divide it into 4 equal parts, and we get the lower quartile, the median, and the upper quartile. If we divide the data into 100 different parts, these are known as percentiles. We're going to be looking at quantiles, and that's where we divide the data into any number of equal groups, but they're mostly going to be percentiles in this particular course. So if we want to find a particular quantile, it's like doing the inverse operation of what we've been doing. So we're going to use the inverse normal function on the calculator. So all we do is go to stats and then hit F5 for distribution and then F1 for normal. We get these 3 buttons. We're mostly using the second one. So for inverse normal, we use this third button. So in one of our previous examples, X was normally distributed with a mean of 13.4 and a standard deviation of 0.2. And the company would like to state that 95% of the bolts that they manufacture have a radius less than K. What is that value of K? So when we put it in here, we've got to decide whether we want the left-hand tail or the right-hand tail. If we draw a quick picture, this actually makes a lot of common sense. So there's our normal distribution. Here's our mean, 13.4. We want some point here, some value of K, where 95% of the bolts lie below. And you can see that it's the left-hand side. It's the left tail. Okay, then we put in the probability or the area under that curve, 0.95. And then just like before, we put in sigma and mu and hit XE and we get 13.7. So what does that mean? It means all of their bolts, 95% of their bolts have a radius less than 13.7. Now there's only one formula that you get on the formula sheet, and that is the z-score formula. All right, let's finish off with a past exam question. This brings in just about every part of probability, actually, this question. It's really cool. It was a calculator question. A nationwide study on reaction time is conducted on participants in 2 age groups. The participants in group X are less than 40 years old. Their reaction times are normally distributed with mean 0.489 seconds and standard deviation 0.07 seconds. Part A. A person is selected at random from group X. Find the probability their reaction time is greater than 0.65. All right, so X is normally distributed with a mean of 0.489 and standard deviation is 0.07. Okay, we want the probability that X is greater than 0.65. We're going to put it in the calculator. It is normal CD variable. The lower limit is 0.65. The upper limit is as close to infinity as we can get. The standard deviation is 0.07 and the mean is 0.489. Hit X here and we get the probability is 0.0107. B. The probability that the reaction time of a person in group Y is greater than 0.65 seconds is 0.396. Find the value of sigma. Now this is quite a difficult question. We have to get the z-score first and then convert it. So this is what it means. Always draw a diagram if you're stuck. So 0.65, we know the mean's 0.592, so that's sitting there. So this is above there. We know the area in here is 0.396, but we don't know standard deviation. So we can't even do inverse normal on it because you've got to put that in. So our only option is z-scores. So the way to do this is by converting to a z-score, which has a mean of 0 and a standard deviation of 1. We're going to use inverse normal. This right tail area is 0.396. Mean is 0, standard deviation equals 1. And that's going to give us 0.2637. So that's now that point there as a z-score. Okay, so it's 0.2637, standard deviations above the mean. There's our z-score. Now we're going to use our formula and z's going to go in there and we're going to be able to find out what mu is because we know x and we know mu. So 0.65 is our x, and then our mu, our mean, is 0.592. We don't know sigma. I'm going to switch these two, and so sigma is going to become, that's 0.058 divided by 0.62637, and there's sigma 0.220. In the study, 38% of the participants are in group X. C. A randomly selected participant has a reaction time greater than 0.65 seconds. Find the probability the participant is in group X. Now this is another very tricky question. This is actually to do with conditional probability. What it's saying is find the probability that the participant is in group X given they have a reaction time greater than 0.65 seconds. So this is what we want. Look at that. Probability they are in group X given their reaction time is greater than 0.65. Just using the formula, we want the intersection of those two divided by the probability the reaction time is greater than 0.65. Now, the probability they are in group X and have a reaction time greater than 0.65, we're just going to multiply 38% by whatever the probability is that their reaction time is greater than 0.65. It was, that's right, we worked that out before. So 0.38, that's 38%, and this was the answer to A, 0.0107. Now, this is going to cause us some grief as well. So what is this? This is the probability that anybody chosen has a reaction time greater than 0.65. Because we've got two groups, we're going to have to do a tree diagram for this. So we've got group X, group Y. Group X could have a reaction time greater than 0.65 or less than. And then from group Y could be greater than 0.65 or less than. Now we worked out these probabilities before and we know this is 38% and so this one's going to be 62. So putting those probabilities in, I haven't worried about these two here. This is going to be this times this or, which is plus, this times this. Let's write that in. Okay, calculating all of that, then the probability is 0.0163. D. 10 of the participants with reaction times greater than 0.65 are selected at random. Find the probability that at least 2 of them are in group X. So what sort of maths is this? This is binomial probability, you know, the last topic. So How good a question is this? It's had conditional probability, normal distribution, tree diagrams, and now binomial probability. This one at least is a little easier. So the probability of success that it is in group X is 0.0163. We just worked that out. The probability that it's not in group X, which we won't use because this is from a calculator paper, is 0.9837. We want the probability that there are at least 2. So we're going to have to do 1, take away the probability that there is either 0 or 1 of them. This bit we're going to put in the calculator. It's going to be CD because it's cumulative. The upper limit is 1. The number of trials are 10 of the participants. The probability of success is 0.0163. Hit XE, we get 0.989. 1 take away 0.989 is 0.01096. Okay, we're done. So here's some of the words that we learnt in this topic. A random variable is the possible outcomes from an experiment. Continuous means within a range. Probability distribution is the probability the variable will take a particular value or values. Probability density function is the distribution of probabilities for a continuous variable. Normal curve is a bell-shaped curve that shows the distribution of probabilities for a continuous variable. Standard normal distribution, sometimes called the Z distribution, is a special normal distribution with a mean of 0 and a standard deviation of 1. A Z-score is a measure of how many standard deviations a score is above or below the mean, and a quantile means to divide a frequency distribution into equal groups.